Hi, and welcome to this course by RouteFabric. In today's session, we'll be covering part 2 of our Data Science in Practice case study. If you haven't watched part 1 yet, you may want to go back and watch that first, as it is a necessary prerequisite to understand what we're doing here in part 2. So let's dive right in. To review, this case study is it's a case study taking us from beginning to end through the entire data science process. I have broken this data science process into 5 stages: capture and collect, and then store that data, prepare and clean the data, explore and visualize the data, and then finally use that data to predict and do something useful for a business. The problem that we are solving in this case study is for an online retailer who sells millions of products, like the 3 shown here. And the problem at hand is to try to figure out a way that we can have machine learning help us to identify relationships among different products. So rather than having a human come in and say, of these 3 possible relationships, the tennis ball and tennis racket are clearly related and might be used as a product recommendation if someone adds a tennis ball to their shopping cart. Instead, we're trying to figure out a way to use machine learning to have a computer decide what these relationships are and how strong they are. Have a computer come and identify this tennis ball, tennis racket relationship as one that is interesting and one that could be used as a part of a product recommendation. So we have collected the data, we have extracted that data into a data warehouse of sorts, and now our next step is to prepare and clean the data so that we can get it ready for analysis. Now, preparation and cleaning is typically 70 to 80% of the effort in a data science project. When we actually just build a model, it is relatively quick, but in order to get ready to build a model and to make some predictions, we have to bend the data into submission, and that data is typically coming to us in very messy formats. I'm going to show a couple of examples here as we talk about preparing and cleaning data, but if you've ever worked with real world data, then you know that it is always messy, and every data set coming from every different system is going to be different, and you have to sort of relearn every time you start a new project with a new source of data. This process is important, but it also is quite time consuming. So some of the activities that we accomplish during this prepare and clean stage are renaming columns, labeling things in helpful ways. Often a transactional system will have columns that are very computer friendly but not very human friendly. And so rather than trying to remember what column is which, it's usually nice to rename data as we're pulling it out to do some kind of a data science project with, to label things as customer IDs and as customer's first name and last name, for example, and part numbers and all kinds of different things. Renaming columns is a way that we as data scientists keep from going crazy, really, because trying to follow a data dictionary like a computer does is very hard for a human to do. Next thing we often have to do is to transform or kind of rearrange the data in a way that is compatible with the analysis approach that we want to use. Often transactional data is stored in what's called long format, where there are very few columns, relatively few columns, and many rows, and each row might represent different portions of transactions that are happening. Typically, when we go to build models, we like our data in wide format. And in other videos, we can dive deep into what long and wide data looks like. But for now, we'll just discuss it in the context of preparing and cleaning the data. And I just wanted to highlight that often we have to transform or pivot the data into the format that is compatible with the approach that we are planning to use. Now we also, aside from just renaming columns, we often will have to format the data in a way that maybe our programming language expects or knows how to deal with. In the case of dates, there's many different ways that different systems store dates. Sometimes it's a timestamp, sometimes it's a count of milliseconds, sometimes the year and the month and day come first, other times they're in different order, and those are going to be different for every system that we have pulled data from. So there's often a lot of formatting and just cleansing of date columns and removing of strange characters and other just formatting activities that we do in order to make the data compatible with our data science process. Another thing that we often do when we are getting data ready for analysis is we're going to pull out and apply different labels. And to explain what I mean by that, here's some sample data that might come from some transaction system. And there's a few ways that we may want to clean up this data and make it a little more useful by adding some labels or doing some formatting. So we've got customer ID, we've got the order ID in a column, and then we've got a timestamp. And this timestamp appears to be a count of milliseconds. That's not very readable, at least for me. Maybe you can read timestamps like this, but I sure can't. We've got customer ID, which is just an identifier for our customers, and then we've got order IDs, and we've got W dash order number, and then we've got an M dash order number. There's a clear pattern to this column. In the example that I'm demonstrating here, I'm going to assume that these orders that start with W for this online retailer are orders that were placed on the web, on the website via a browser, where the order IDs that start with an M are stored as orders that have been placed via some mobile app. That's just a hypothetical situation, but that's useful to me. But rather than trying to remember what order IDs are and that W means a web order and the M means a mobile order, part of the cleaning process would involve me extracting out that information into a separate column that I could use in my analysis. So I might add a column called order type that uses some logic or some rule to say if order ID starts with a W, then this variable is going to be a web order. And if it starts with an M, this variable is going to be a mobile order. This is something that's very useful to me as a data scientist, as an analyst. I can categorize things by web and mobile. I could visualize and do bar charts or look at trends within these different categories. This is very usable, whereas this order, this information embedded in this order ID is not especially useful to me. So that's one example of activities that we might do during our prepare and clean phase of an analysis. Second example is having to do with that timestamp column. Now again, this is not a very readable column. I don't know how many milliseconds this has been since the year 1970. And so I might apply some logic to extract out the day level information. In other words, I just need to know the day of the month in a particular year that these orders happened, because this is much more useful to me as a human. I like to think of things in terms of months and days and years, and I don't like to think of things in terms of milliseconds. Computers like this column, and I, as a human, much prefer this column. So this is something that I might extract out in order to help clean and prepare the data for a good analysis. So these are just two simple examples. Typically, as we go through and do this cleaning and preparation, we're going to add dozens of columns and or potentially just reformat dozens of columns, probably both. And those columns are going to be what I can then use in my analysis because they're columns that I trust. I know what's in them. I know how they're formatted. And that allows me to be much more effective in my data science process. So that's the prepare and clean stage. And again, that's the third stage. And if you've never done a real analysis with real world data, then you'll just have to trust me that this prepare and clean phase is typically at least 60, if not 70 or 80% of the effort, and takes a very long time. But it's a good place to spend time because the more effort you place in this process here in the prepare and clean stage, the easier and cleaner your processes are going to be in these second two stages. So we'll move now to the explore and visualize stage. It's during this phase that we really get to know our data. And what I mean by that is I like to understand when I have a data set, I need to understand how it behaves. And I need to understand what variables are in the data set and just how they are formatted, how they look, what their distributions are, whether they're almost always 0 and only occasionally a 1, or maybe whether they're just they're skewed in some way. All the different columns in a typical data set are going to look differently. So these distributions, I like to look as I explore and visualize. I like to just graph distributions, maybe by category, or depending on how many columns there are. I just will create distribution graphs or distribution density plots and look at the distributions of the various columns and ensure that there's no columns that I feel funny about or that I don't think will work well in an analysis. So distributions are one thing that I check. I might also be very interested in how much data is actually there. Typically in a data set, we're going to, this is a statistics term called missingness, and it doesn't roll off the tongue very well, but it basically just means for some observations in my data set, I'm going to be missing certain points of data. Maybe if I'm looking at web traffic data on information from the first page is going to have much more information typically than maybe data all the way at the end on my checkout page. More people spend time on the first page or so of a web transaction, and then they'll drop off. And so if I'm, depending on how my data is structured, if each row of my data set is defined by a session or a person interacting with my website, then I'm going to have a lot of empty cells or empty data over in my the latter pages of my data set. And that missingness is important. There's many algorithms that we might try to run in our data science process. They actually expect there to be no missing data because it makes the math kind of hard. And so missingness is something to be aware of, and there are processes that we go through to eliminate missingness by essentially filling in the missing values or excluding them. There are a variety of ways to handle this problem of missingness. But it's something that in this explore and visualize phase, I just want to become familiar with how much of the data is there, and for certain variables or columns are going to be more missing than others, and if there's certain columns maybe that are fully missing for some reason, or maybe in the narrowed set of data that we've pulled, those columns just aren't valuable and they should be excluded. These are the kinds of things that I am looking for and trying to understand during this explore and visualize phase. As a part of these analyses, I'm also going to be generating things like summary statistics, the averages and the minimum and the maximum and median values, and either charting these or looking at them in a table. Depends on the magnitude of the data, but I'm going to want to understand what these values are and what the different columns contain. Frequencies is another way to think of this. Maybe frequency of a binary variable, like that mobile and desktop column that we generated in our prior example. I might be really interested in understanding what percentage of my data is from the mobile traffic and what percentage is from the website. And that's not because that's an interesting research question, but it's really because if I have 99% of my information is from a mobile app and just 1% comes from desktop, then that's important for me to know. I might need to treat those desktop observations differently depending on the modeling technique that I'm using. So understanding those kinds of things is important, and that's what we use this explore and visualize phase for. It's really just me becoming familiar with the data. Now, often as I'm doing these various things, there's going to be a lot of charts that I generate, and every data scientist has a different way of going about this, but I will frequently do density plots, and I'll do lots of bar charts, and I'll do box plots. It depends on the situation, but I will use a variety of charts to just explore and kind of visualize what the data looks like, and you'll see a lot of those in this stage of data science. Now, if you remember from another video that we've done in this series, often, in addition to just looking at distributions or looking at summary statistics, it's useful for me to start exploring possible relationships or just possible trends in the data in this phase where they might be applicable to my research problem. So this is where I'm going to be looking at and typically visualizing in charts of some sort some variable summarized by some other grouping variable. So that example of maybe the number of sales or transactions per web or mobile app transactions. That would be me summarizing the sales numbers by that order type variable. In the context of our product recommendation, I might be just interested in understanding the number of sales by different product categories and trying to understand where my spread is, where most of my transactions are, and where I maybe want to focus my modeling efforts, for example. I might be really interested in looking at things not just by different categories, but over time as I'm trying to understand trends. Particularly when I'm trying to be predictive and build a predictive model, it's really important to understand whether time plays a role in whether things change over time. And if the data that I'm looking at to build a model is no longer applicable because things have changed in the last 4 months, that would be really important for me to know as a data scientist. Lastly, I might be interested in just exploring possible relationships, and you can do this by simple correlations, often graphing relationships between two different sets of variables is useful to see whether there appears to be a linear or some other kind of relationship between two variables. Typically, I'm going to focus these observed relationships on things that are relevant to me and that are interesting to my research problem or the thing that I'm trying to solve. And those are the kinds of things that I'll do in addition to just getting to know your data. It's really starting to understand with some really light analyses possible relationships and other things that might live in the data that you're playing with. Now, it's important to understand that this explore and visualize phase almost always will create understanding, and it will create a situation where you learn that you have to go back and do some additional data cleaning and data prep in order to fully represent something. So, for example, if I didn't know about that order type difference in our example, and I didn't know that there were mobile and web, and I discovered that 40% of my order IDs started with M and 60% started with a W. That's maybe something that I would learn in this explore and visualize phase. and I would go back and iterate back to the data prep stage. I'd redo some of my cleaning and set up maybe additional rules to add clarity and add additional columns and features to this data set. And then I'd go back to the explore phase. And I'm usually bouncing back and forth between data prep and explore and visualize until I'm really comfortable with the data and until I really understand and know what it looks like and how it behaves. Okay, so it's during this explore and visualize phase, if we move back to our analogy, that I'm starting to understand some of these relationships, but I haven't taught my computer, my machine, to do any of these relationship finding activities. All I've done is I'm understanding what is available in the data so that I can use some of that to teach the computer or the machine to start to identify some of these relationships. So that brings us to our final and most exciting stage in the data science process, which is where we actually build and evaluate predictive models. That's this final stage where we're going to predict and use a model to accomplish our problem. Now, at a high level, this predict and use stage is where we do basically three things. First, we're going to use, now that our data is ready and that we understand it, we're going to use an algorithm, sometimes 2 or 3 or 4. We're going to use one or more algorithms to explore relationships or to explore the structure in the data, some pattern in the data that we are trying to identify in order to solve a problem. And we'll apply this in just a moment to our product recommendation case study. But at a high level, we're going to use an algorithm to try to explore some relationship. We're going to then, within that algorithm, or maybe across a few algorithms, we're going to iterate typically and adjust or tune the algorithm, tune the model that we're building with various options and parameters that allow us to make sure that the predictions that we're making are as accurate as possible and that the model is the best that it can be. So that's the second piece. And then lastly, once we're happy after iterating quite a few times on a model and tuning its parameters so that we're happy with its performance, we're then going to choose a final champion model or a set of models, depending on what we're doing. And I'm going to use the word deploy. We're going to deploy that model so that it can then be used to aid us in the decisions that we are trying to make. Okay, so this is the predict and use phase at a high level, and this is where it gets really fun. This is why people do data science, because predicting things with some level of accuracy produces a ton of value. It is the reason that we do what we do in the data science field. Now, we're going to take our model building process through this flowchart so that we can understand what's going on. There's some assumptions here that we have already prepped our data and that it's ready to go, that we're ready to build a predictive model, and we have understood, and we have as a goal, we have some objectives or the business problem that we are going to solve. So those two pieces of information or constructs, I guess, will feed into and serve as inputs into our model building process. And so as we described on this previous page, we're going to use an algorithm or several algorithms to explore some relationships. So we're going to design a model. We're going to choose an algorithm that fits the business objective, and we're going to apply that algorithm or that model to the prepared data. And then we're going to let the computer follow the algorithm and find whatever patterns the computer can find. We're going to evaluate and validate the results of that model and decide whether we are happy with the results. And what that typically means is we're going to look at performance measures, such as accuracy, or there's a lot of model fit features or metrics that allow us to say, yes, given the thing that we're trying to the pattern that we're trying to find, we feel like we're being pretty accurate here, or we feel like we are accomplishing the purpose of the model. We also might evaluate the results of our model in terms of something called face validity. That's an academic term, and forgive me, I'm an old academic, and during my PhD studies we talked a lot about face validity. Does the answer that a model is providing, does it make sense just at face value, is the way to think about that. Is it something that a normal person would look and see the prediction from that model and say, oh yeah, that makes sense. That's face validity. And if a model doesn't make sense, just sort of to a human in general, then it might be suspect, and it might be something that we want to think about. We're going to evaluate models in terms of either their stability or robustness, meaning would they hold up over time? Would they, if we used maybe the data that we have from the year 2019, and we tried to predict everything that we have seen so far in the year 2020, what does that performance look like? Does the model hold over time, or is it only really useful during the year 2019? Or maybe we build this model and it's only going to be useful for half of our products, and we try to apply it to the other products in our online retail store, and it just doesn't work, and it doesn't predict anything useful. There's a lot of different ways, depending on the context, that we're going to try to evaluate and decide, is this model good? That's the basic answer that we're trying to come to, and that question is an important question, and it's basically us saying, is this model going to be useful for the business, and can I trust it over time? Now, typically, when we design and test our first model, the answer to some of these is going to be no, or it doesn't pass, or it's otherwise not as good as it could be. And so we're going to, following our step back here, we're going to successively iterate. We're going to adjust some things. We might choose a different algorithm, for example, or we might just change some of the parameters, some of the settings, so to speak, within the model, and make adjustments, and then redesign a new iteration, and then evaluate the new one along these same criteria until we cycle through this enough times to the point where we are happy with it. Once we get to the point where we're happy with it, again, this third stage is we choose a model that's our favorite, that we decide is the best, that's either the most accurate, or it makes the most sense, or it's the most stable. Whatever our criteria are, we're going to have a winner. At least we hope that we have a winner, because that's why we're doing this data science project. And as a result, we say this model is the winner. We're going to deploy that model. And what that really means in practice is that model then becomes an API endpoint. And if you're not especially technical, that just means that there's a server somewhere that you can send a question to, and then that server will give you an answer. So to give you an example, once this is done, once we've finished our model building process and we have deployed our model here as an API endpoint that our systems can interact with, then the model's ready to use to try to make future predictions. As we evaluate the model in here, the model is being trained. We're teaching the algorithm how to identify, in our example anyway, how to identify which products are related to each other. We're gonna use various algorithms to kind of reveal those relationships. We're gonna evaluate them, and then we're gonna say, okay, we feel pretty good about this, and we're going to deploy that model. And what that allows us to do is, in the future, let's say a week later or so, there's going to be a new observation. And what that means is, rather than the historical, prepared, beautiful data that we used to build our model and to try to teach the machine how to do something, we're going to have a new order come in next week. And as someone's going through and making that order, that's going to provide a new observation. We're going to take that information and send it to that API in the form of a question and say, hey, here's some observed data. Can you use the model to make a good prediction? that API, that deployed model, that API endpoint is going to send us back a prediction, and that is how we use a predictive model to predict things in the future. We establish something that that is based on historical data, based on our best guess, essentially, and then we can use that model later, a week or a month, or maybe for years sometimes, to evaluate and get predictions about how we might treat these new observations. Now, this model building slide is quite conceptual, but hopefully it's a useful depiction of the basic process for actually building and deploying and using a data science model. Let's apply this concept now to our online retailer and product recommendation use case. Now we're going to remain a little bit abstract, but what these dots represent are products. Each of these dots is a product, and you might think of these products as being as having various features, maybe their color and their size and their weight and what they're used for and who buys them. When a model algorithm looks at these different products, we're going to give it a lot of information about those products, and we're going to give it information, for example, about when people buy these products, which products are typically bought together in the same order. And if you're a big online retailer and maybe you've been selling a number of products for about a year, then some of that information might be useful to help us to add some groupings to this model. So let's assume that we have gray, colorless products that again, we as humans, we don't want to go through and decide which of these products is similar to each other and which ones are different. We want to have a computer program do that for us. We want to teach the machine and have a machine learning algorithm solve this problem for us. So let's say that this dot represents a tennis ball product. This dot up here represents the tennis racket. This over here represents our microwave from our initial scenario. Now, as humans, we can't look at these and tell them apart, and we don't want to find the relationship. So we can apply our model to this data, and we can let very sophisticated algorithms solve this problem for us. Luckily, in data science, we're almost never the first person to ask any question. And so someone has solved problems like this before. So we can use an algorithm that someone designed that helps group things into like groups. That's a clustering algorithm. And in this case, it's a really great algorithm to use for this product recommendation use case. So if we apply a clustering algorithm to the set of products that we have, we might learn about which ones are similar. These colors are designed, are intended to sort of display the different groupings. And based on a variety of characteristics, some of which may make more sense than others, but based on a variety of characteristics, this algorithm might tell us that these three things are related in some way. I don't know what these three things are, but they're yellow in our example. These three things are related. And these blue things, as you can see, are probably related to maybe tennis or maybe even sports or outdoors. And an algorithm might allow us to identify that relationship without us, the humans, having to go through and look at each of them and say, oh yeah, that's a tennis ball, that's a tennis racket, there's a soccer ball, and there's a pair of gym shorts. And all those things are related to doing sports outside. We as humans can do that, but when there's millions of products and the products all have different features, we don't want to have to do that. So we use an algorithm to classify or to cluster these things into different groups. And in this case, our blue group, we'll say that represents maybe sports equipment of some sort. So that's good. You'll notice that algorithms, maybe this pink one down here, is kitchen items or something that goes in a kitchen. And those pink things are, maybe this is a fridge, and that's a microwave, and this is a set of mixing bowls or something. And because those things are related to kitchen, the algorithm might detect that and place them in a group and allow us to use that information. Now, if we apply this to our historical data and create a model, deploy that model like we did in our last slide, then this green box represents a deployed model. It represents our understanding of our products and the groups into which each of these products might be placed. What that allows us to do as our online retailer, again, maybe a week later, we have a new observation. We've got someone who added this thing to their cart. Now it's gray. We don't know anything about it, and we don't want to go in for every item that's added to carts. We don't want to have a human come in and say, oh, they have added this thing. I think that we could recommend to them that they add something from our inventory to try to increase the value of the sale for that customer. What we can do, though, is use this observation, send it to our model, to our deployed model, and say, hey, model, can you give us a prediction? It's an observed data that we send to the model, and we say, given the characteristics of this observation, into which group is it most likely to fall? And if our model is a good model, and if we can trust it, the prediction that it might send back, if this observation, if this product is tennis shoes, it's not something that it's not a tennis racket, and it's not a tennis ball, but our model might indicate to us that, hey, that belongs in that blue group up there. Maybe this guy is tennis shoes. And it's going to say, hey, that's a blue thing. And then we can use this prediction as people are adding things to their cart, to their shopping cart. We can then make recommendations, and we can say, that is a blue item. Those are tennis shoes. I am going to suggest to you that you might also want to buy other things from that blue group. That's a tennis ball and a tennis racket. This, if you've ever shopped on Amazon, this is, in essence, what Amazon has done. Amazon understands lots of things about the products that they sell. They understand trends on who buys what with other products, and they've got massive amounts of data. And one of the things that they do when you add an item to your cart is they make a recommendation saying, if you added that, you may be interested in this other thing. And often they're quite related, and if you're like me, then you end up spending more money with Amazon because they're very good at what they do. But if we're the owner of our online retailer, then we are very interested in extracting additional revenue from each of our potential customers. So a machine learning algorithm like this that we carefully build and then deploy so that we can use it in the future to make predictions, that becomes something very valuable to us. So using this end-to-end data science framework, we have now gone through all of these 5 stages of our data science process. We've captured and collected the information from our various systems. We stored that in a data warehouse or a data lake, made it available to us for analysis. When we were ready to go and try to make some predictions, we first had to prepare and clean the data, and then we went through this exploration and visualization process, looping back to preparing again, and then going again to exploring and visualizing, and getting ourselves familiar with the data and getting the data fully ready to build a model. And then we used our model building framework to build and iteratively evaluate and improve a model till we finally found the right model that we were going to use to solve our problem. That model was deployed, and then it can be used to predict things in the future that allow us to make more effective business decisions. as we invest in this data science process, increasingly with the amounts of data that are available to us and the sophisticated processes that we have to train models and algorithms with increasingly large amounts of data, this becomes a very lucrative and powerful thing that businesses and other institutions can apply to help them achieve their goals. I hope this was informative. If you'd like to know more about the data science workflow and about data science in general, you can check out our other courses on RouteFabric.com. Thank you.